Hello everyone, welcome back. Boy, do I have a spicy one for you today. But first, we need to wrap up our Recursion one allStar. This is the one I assigned you right before we left off, given a string. Compute recursively a new string where all of the adjacent chars are now separated by a asterisk. So we're taking in a string and we need to basically just separate these bad boys, every single character. This one, not too bad. Like a lot of the string ones that we have been working with, we're going to consider one character at a time and then chop it off and keep going. So I'm going to, eventually, if I just keep chopping off characters, I'm going to run out of characters. My string won't have anything there. So if our string length is 0, then we're done. I'm going to return effectively nothing. Okay, so this looks like a base case to me. We may be able to consider something else, but I like to basically start out with what I expect the base case to be and then look for shortcuts from there. So if I'm still in the method, that means that I have a character to consider, and this one is pretty repetitive. So all I'm going to do is return. I can already see a catch coming in here. We're going to return the current character along with an asterisk. And we want to keep going, but I've already used the current character, so I want to shave that off. We'll call allStar, passing in str, slightly shortened. All right, let's give this a whirl. Right, you see these errors where I've messed up. Right, I got one. We got one here. Extra little asterisks here at the end, because if you look, what we're doing is taking the current character and then attaching an asterisk and then continuing. The problem is when I'm left with one character. So to me, help me out in chat, but to me this seems like our base case is not when we have no characters left. I'm thinking maybe our base case is we only have one. If our length is less than or equal to 1, here I'm doing less than or equal to because I also want to consider the case where there are no characters. We see that that is a test case that they're giving us. Okay. If my string length is less than or equal to 1, that means I either have one character or no characters. I'm going to return the string as is. Ta-da. Okay, this one wasn't bad. Just that little niche test case where we have to change our base case. Let's get to the spicy stuff. See ya, CodingBat. Today we're talking about Towers of Hanoi. I would not be a good computer science teacher if I didn't talk about Towers of Hanoi whenever we talk about recursion. And you all know I'm the literal best teacher. So let's take a look at this. Towers of Hanoi is a puzzle game that involves moving disks from peg to peg using certain rules. This game, its story, and its recursive solution to solving the puzzle has become famous amongst the computer science community. Despite being a simple puzzle game, a fable has been fabricated to add background to the Towers of Hanoi. We wouldn't have a good story without plot, right? Many centuries ago, in the city of Hanoi, Vietnam, monks in a certain monastery began acting upon an ancient prophecy. Ooh. I really should get Mr. Taylor to voice over this. Maybe I just go through with this and I just come back and add his voice. Still my face, but his voice. 3 large posts were erected in the monastery and 64 discs of increasing size were placed on one of the posts. The prophecy instructs the monks to move the disc from one post, presumably this leftmost boy, to another post, presumably the rightmost post. So it doesn't really matter what your start and end post are, but kind of in practice what I see is that we take them from this left post and we move them to this right post. However, there are 2 rules. Only one disk can be moved at a time, and a larger disk cannot be placed on a smaller disk. We'll take a look at that. The monks believed that the world would end and humankind would be freed from suffering when the task was finally completed. The fact that the world is still here, and you must endure the frustrations of hearing this story may lead you to believe that they were wrong. However, math has proven that the minimum amount of moves required to move all 64 disks from one peg to another under the constraints provided would take this number. At the rate of one move a second, which you can't go that fast, it would take the monks about 585 billion years to move the disk, which is roughly 127 times the current age of the sun. Lucky for us, computers are capable of processing several moves a second, so we don't have to wait for Vietnamese monks to discover the end of the world. I want you to play Towers of Hanoi. Okay, there's a couple of links here embedded in the slides. I recommend the Cool Math Games one. That's the one that I like. So I'm going to pull up a browser. We're going to throw in some Cool Math Games. Cool Math Games. What are we doing? Towers of Hanoi. Let's go. What is this? Are they telling me to... I just want to play my game. Let's figure this. Allow flash. Just play my game. What if I don't have flash? I thought they converted all of Cool Math and it's not flash anymore. Well, maybe I do the other one. Because I don't really want Adobe Flash, I'm not going to lie. Let me grab this link, question mark. Here we go. Alright, I'm off you, Cool Math Games. So, this is our Towers of Hanoi. I recommend 3 or 4 discs starting out. We need to basically first learn the rules. So, our goal is to get all these discs from this leftmost to this rightmost. My only 2 rules is I can only move 1 disc at a time. And I can't put a larger disc on top of a smaller disc. So this is an illegal move, right? It just literally won't let me do this. So what ends up happening is you use one of these pegs as a spare peg to kind of make your moves, right? So now I want to move this bad boy, but part of my problem is I can't put it on top of either of these. So what you have to do is take one of these smaller discs and free up a peg to allow you to move over a deuter. Now, I'm not doing this the best way possible. I'm going to claim that's on purpose, right? I believe it specifically wants me to get all the pegs here onto this bad boy. Well done. 14 moves. Let me get some poggers in chat. I want y'all to play around with this for a little bit. Let's up it. Let's up it to 4 disc. Is that a thing? Ooh, yeah. How's everyone doing today? Well done. There are some references to this in pop culture. The Planet of the Apes remake. They were using this as kind of like an intelligence test. I think something like Rubik's Cube is way more challenging, way more testing of intelligence. Well done. Minimum move 63. Oh, I do kind of like that it tells me what the minimum is. Didn't know we're going to have a Towers of Hanoi stream today, did you? I'm going to make like front page of Twitch or something. Only 7 discs in Towers of Hanoi? Those are rookie numbers. You gotta get them numbers up. He's going the distance. I want you to see minimum number of moves is 63, and my moves is 63. Okay, let's continue on. So that's Towers of Hanoi. The math shows that the minimum amount of moves required is 2 to the n minus 1, where n is the number of discs. So we can just always figure that out. We saw that the Math is Fun version actually tells me how many the minimum moves. That's kind of nice. This problem is famous amongst the computer science community, not because the computer can actually process all the moves in a lifetime, but because the iterative solution is incredibly cumbersome compared to the recursive solution. This is the quintessential recursion problem. I get it. Like, I'm not a big fan of recursion. Everyone always asks, why do we have it? Why do we got to learn it? Why does it even exist? And I get it. And I'm telling you, the reason it exists is basically this. There are certain problems, such as Towers of Hanoi, where the recursive solution is so elegant that it kind of warrants recursion existing. The iterative solution is just like a hot mess. So here are some iterative solutions. These are bits of code that are going to basically tell you. When I say solution to Towers of Hanoi, it's basically we're going to write a program today actually that'll tell us the moves. It'll tell us what we should do. And it's going to do that via print statements, SOPs. Now, if you basically replace the print statements with literal moves, you could write a program that would actually do the moves, digitally, right? Tomorrow, I got something lined up for you that's special. We're going to be using some Java FX. You could, in theory, make a GUI, some type of animation, graphic user interface, and then have it play Towers of Hanoi for you. And it's effectively the exact same solution. Let's look at these iterative solutions. Right, these are there's not a lot of these online. This one's got some variables. You can kind of ignore the try catch, but here's our iterative solution. It's a lot of text. Here's another iterative solution. Again, I didn't find a lot of these because people don't solve this iteratively. I kind of want you to know, this is the sample output with like 3 or 4 disks. I basically just want you to note how much text is going on here, right? We got a lot of lines of code. It's thick. All right, you ready? Whoops, fat fingered that. So those were iterative solutions. They're a hot mess. Let's look at the recursive solution. This is it. This is all of it. I can fit it all into one slide. This solves Towers of Hanoi. I have one line to iteratively. You jerk. let's code this. Let's code this in IntelliJ. I'm going to throw that bad boy to the side. We're going to open up some IntelliJ. Great Fox. You know, I don't know why my taskbar is white. Recently upgraded from a hard drive to a solid state, and so it's a relatively fresh Windows 10 install, which is why I don't have Adobe Flash. Yeah, I'll fix it eventually. It hasn't bothered me that much. We're going to, in IntelliJ, I'm doing a file new project. We're going to go next. We're calling this one what? Towers of Hanoi. This is just the name of my folder, so we can have some spaces there. Okay, I'm going to expand my project folder. Right click on the SRC. Let's do a new Java class. We can call that driver or Towers of Hanoi. I don't really care. Doesn't matter. I'm going to plug in main method. We'll come back to it though. So PSVM will give me a main method. And let's write this move method. Right, our header, public static void move. So this is just going to be printing out my moves as we go. We're going to have a couple of values. We have an integer n. What do you think n is? We're going to have a couple of things that represent my pegs. So we have our from peg, our other peg, which is kind of the spare peg, and 2. Now, we could use strings here. I'm a big fan of the chars. Very simple. These chars are representing my pegs. So we'll effectively come in and label them. And what we're going to do is label them A, B, and C. Right? The leftmost peg is going to be A, the rightmost C. So n is my number of disk. Let's maybe Java doc this. N is number of disk to move. From, this represents the peg the disks are moving from. Other is the spare peg. And 2 is the peg the disks are moving to. So that's what these parameters mean. And I'm using chars to represent that. Again, you could use strings. So if we only have one disk left, that is n is less than or equal to 1, it should never actually be less than 1. But again, I like to encompass all of my possibilities. We're going to sout move, right? This is going to print off the moves. N, so it sounds like number of pegs. In some context it is. Here in the SOP, what n is effectively if we numbered the peg, right? I believe with the smallest peg, or sorry, this, not the peg, the disk, is as if we numbered the disk, with the smallest disk being 1. Okay, we're going to move disk n, 1, 2, 3, whatever, from the from peg to the to peg. Okay, bear with me. So that is our base case. If we're still here, right here I'm using an else and not just going straight to a return, and that is because we're printing, we're not actually returning. So the else is going to be, here's a recursive call. We're going to call move, passing in n-1 from to other. Okay, notice that this order looks like it's changing. And what I'm actually doing is in this recursive call, I'm switching up. The from peg is going to be the same. We're going to see this. I've got a good visual to kind of help us with this. The other peg, what was the spare peg, what was the to peg in this call is going to be the spare peg in this call. And what was the spare peg in this call is going to be the to peg in this recursive call. Again, when we get to the visual, it'll help. Here I have a sout, and it's, I believe, just literally this. And then there is a recursive call. So this is not tail recursion, right? When we first learned about recursion, we talked about tail recursion where the recursive call is always at the end. Here I've got a recursive call, some more stuff in a recursive call. These are harder to turn into iterative solutions. And so as I said in the slides earlier, they are justifiably recursive. This is a good recursive problem, largely because it's hard to get an iterative solution. That's the reason that recursion exists. But notice in this recursive call, again, the pegs are switching up. The other peg is actually going to be my from peg. I'm going to take the stuff from the other peg using the from peg as my spare peg, and it's going to the to peg. Okay, here's the solution. This is it. This is everything. This will solve Towers of Hanoi for us. So what I want to do is come up here. Let's make an initial call. I'm going to call move, passing in, let's say that we want to do 4 disk. I'm going to have 3 pegs. I'm going to label them A, B, and C. Okay, no need to put this in a print because all of my printing is happening down here in this move method. I'm going to right click in free space, tell this to run. Whoa. This is telling us how to solve Towers of Hanoi in the bare minimum moves. So why don't I follow these directions? Let's kind of zoom out a little bit here. So I'm going to go to 4 disk, right? That's what we're doing over here. And I'm going to follow the directions. It says move 1. Oh, don't click with. Move 1, that's this little disk here, from the A peg, that's this one on the left side, to the B peg. That's my second one, or the spare peg. Sweet. Move 2 from A to C. Move 1 from B to C. Move 3 from A to B. Move 1 from C to A. Okay. Move 2 from C to B. Move 1 from A to B. Move 4 from A to C. Move 1 from B to C. Move 2 from B to A. Move 1 from C to A. Move 3 from B to C. Move 1 from A to B. Move 2 from A to C. And move 1 from B to C. Well done, right? Minimum number of moves. Okay, so this tells us how to solve Towers of Hanoi in the minimum number of moves every single time. And while I'm printing here, what you could do in theory is turn this into some type of graphic, right? You can make some type of animation. It's actually pretty impressive. And we could, like up this. Spoiler alert, this takes a while. Even with the computer being able to go insanely fast, right? Doing several moves a second, This can take some time. I believe I've done something like 32 or something like that, and it took like a day and a half, basically a weekend. I let it run over the weekend to solve. So this takes some time. Now, to be fair, what really takes time is printing to the console. I mean, it's actually able to do the math and all of the recursive calls really fast, but literally printing to the console takes some time. But I mean, if you're not going to do that, then what's the point? So if this is something you're interested in, yeah, I would maybe throw a timer in on this, right? Why don't we actually kind of show how to do that? Yeah, let's. I'll go back to my move method for a moment. So what we can do is add a timer to this, and we've done timing before a lot with our sorting algorithms, and basically it works like a stopwatch. I want to figure out the time before my initial call, and then figure out the time after that, find the difference. Okay, so I'm going to move back up to my main method, and I'm going to plug in how we can time. Now, time is measured in long, like always, because what it effectively is number of seconds that have passed since January 1st, 1970. So I'm going to have a long for my start, and we will call system.current-time millis. Right? This is going to give me in milliseconds. You can get more accurate by doing something like nanoseconds, but it's a little bit unnecessary here. And then I'm going to have a stop. Notice this is, right? Like I'm going to clock my time whenever we get started. I'm then going to have it do the recursive nonsense, and I'm going to clock my time whenever we stop. And what I want to know is how much time has passed. So let's do something like time elapsed. And we just take our stop minus our start. What don't you like about this? What if I did this? Sweet. Okay, I'm going to test this. Let's do like 4 disk. And so we can see how quick this is able to do this. So this is 49, let's annotate this, 49 milliseconds, because that is essentially the method I'm using is giving me the current time in milliseconds. What it is number of milliseconds that have passed since January 1st, 1970. I get it here, I get it here, I find the difference. It's just 49. It's just 49. I've heard your science teachers talk. I know that they want you to put units. Let's just put it that way. So let's amp this up, something like 7. Right, 55 milliseconds. It's pretty fast. Something like 17. Okay, so we kind of talked about using time in CSP. It's not a good measure of algorithm performance. That's largely because, right, hardware differences. That is a big reason. And even within the same machine, right, if at school we have essentially all the same computers, yet if you were to run this, you would still get different times. And that's due to maybe, resources. Maybe you have Minecraft running in the background, Carson. And so that could like be taxing on the system and taking up resources, that sort of thing. Maybe you've got a beefier machine than what I have. Anyway, so this is how we can time it. So I kind of want to talk about this. I have a visual that'll assist us with this move and kind of show how it all works. So let's hop back to our slides. Right, the brilliance of this recursive solution is in how elegant the code is written. The method call, for example, says move n-1 disk from the from peg to the other peg. Let's get like our visual here. Let's restart this bad boy. So in order for me to move this bottom peg, I have to first move all 3 of these. Right? In essence, this is saying take 3 disks from the from peg A, and it needs to go to the other peg. For me to move this 4th disk over to here, I need to get these 3 disks to here. that's kind of what this is saying. Let's take 3 disks from the from peg, put them onto the other peg, right? Keep in mind that in this order, it's from, other, and to. From, other, and to. So this recursive call is taking 3 disks using from the from peg, and it needs to go to the other peg. Move these 3 disks here using this bad boy as the spare peg. Okay? Then move disk in from the from peg to the to peg. If I'm trying to move these 4 disks, right? Ultimately, the 4th disk needs to go here. That's what happens with this print. It's telling me to make that move. Let's move, once we have moved these 3 to the spare peg, let's take disk number 4 and move it to the destination peg. Now, move n minus 1 disk from the other peg to the to peg. Okay, so let's kind of perform this. So I want to move these 4 disks. What I'm going to do is effectively put these 3 onto this spare peg using the other peg, sorry, using the to peg as my spare peg. Okay, we did that. Now let's move disk 4 here. Okay, so we're in this scenario whenever we hit this last recursive call. Oop, wrong one. This says move n minus 1, 3 disk from the other peg to the to peg, right? Notice that these 3 disks are on the other peg. I want to take them from there, from the other peg, to the to peg, using this as the spare peg. That's what this is saying. Okay, if we were to actually follow it, let's use a move 3. We'll step inside this recursive call. We'll ask, is n less than or equal to 1? It is not. So we hit this else, where we're going to move n minus 1 or 2 using this setup, right? My from peg is going to stay A. My to peg is going to be B. So we're using C as the spare peg. Let's step inside of that call. We would ask, is n less than or equal to 1? Nope, we hit this else. Notice that I have a call, like this is starting to stack up. Okay, we'll step inside that call. We would ask, is n less than or equal to 1? Okay, it is. Let's print our move. It would say move 1 from A to C. I go back up here to move 2, right? Move 1 finished out. Move 2, I can start to solve it. It's going to then print a move. Then I hit another recursive call. Well, let's step inside that. I would ask, is n less than or equal to 1? It is, so we print off our move. At that point, move 2 is finished, right? We did move, print, move. I'm back up in move 3, where we've done move. We just did print. I need to perform this bottom move. We're going to put a move 2 on the stack. We'll step inside that recursive call. We would ask, is n less than or equal to 1? It is not, so we hit this move, right? This move 2 needs to do basically move, print, move. Here's the move. We would ask, is n less than or equal to 1? We print that off. We then print the move. We need to do another move, which is a move 1. And then finally, this move 3 is completely finished. I know that was very haphazard because we don't see a lot of these, right? Like in theory, the AP exam wouldn't have a lot of this going on. This can get pretty hard to kind of trace, but that's what's happening. I put code onto the stack. We then solve more code. We come back. We try to finish what we can. Anyway, the whole point of all of this is to show you Towers of Hanoi, which has just the ridiculously clean recursive solution. What's the point of recursion? This is the exact scenario. right? We have a problem where the iterative solution is just, it's hideous. It's gross. It's very disgusting. Here I have a recursive solution, which is very clean. It fits on one slide. And in a lot of ways, it could actually be intuitive. It could be arguably more intuitive than the iterative solution. Guys, that's going to wrap us up. This has been Towers of Hanoi. I don't really have homework for you. You can do some coding bats if you want, but we're just going to chill. Tomorrow, we are doing, again, something kind of fun, some fractal trees. I will show you how to do that using Java effects because it is very visual. To answer your question, the AP exam is over the first 7 chapters according to their curriculum, which is up through maybe 2D arrays. I got to double check that. But you won't have multiple choice. It's going to be purely FRQs. That's good in a lot of ways, in my opinion, because reviewing FRQs is much better to do in this type of platform, right? I've done some FRQ review via Twitch before, and that comes off like very well because I basically just solve the FRQs in real time in front of you, and you get to hear like my train of thought. And I actually think it's a very good. This is good. Yeah, it's way better than multiple choice questions. For now, Daniel, what did you ask? Sorry. No, I'm not switching the times. All right, let's chill.